Okay, hi everyone. So welcome to our third attempt of this lecture. So basically today we'll discuss about the efficiency of algorithms. But before we start, basically a short update. We will start using from today Zoom instead of Google Meet. And the reason is that Google Meet will disable recording starting September 30. However, for office hours, we'll continue to use the old Google Meet since we basically don't record them. And that is updated both in the Piazza Zoom instead of Google Meet link and office hours link, both for me and for my TAs if you want to set up an appointment with my TAs. One other thing that I want to discuss is that today there is also a quiz. And for this quiz, I actually provided answers. So all that you basically need to do is to review the quiz, which we'll do together at the end of the class, because today it will be the first time that we will do the the efficiency of algorithms. I'm just checking one more time that it's still recording. Good. And then we'll basically do the lecture for today, the efficiency of algorithms. I hope that you can hear and see my screen now. Is that true?
Yes.
Okay, excellent. Thank you very much. So as I said, today we'll actually learn the big O notation, which is in fact the growth rate of an algorithm and the measure of the growth rate of an algorithm. We will talk about complexity of various types of algorithms. In particular, we'll discuss the complexity of binary search, selection sort, insertion sort, and the towers of Hanoi, and various growth rate functions, constant, logarithmic, log linear, quadratic, cubic, exponential, and linear, in fact. Next class will basically continue with more topics on efficiency of algorithms, the efficiency of Fibonacci numbers using the recursive implementation, and then an optimization of Fibonacci using tabling or memoization, basically saving the results of calls that were already seen. Also, we will learn about other techniques of developing algorithms like dynamic programming, divide and conquer, and backtracking. But let's start with basics. Basically, an algorithm. An algorithm is basically a mathematical process to solve a problem. And algorithm design is this development of the mathematical process. Algorithm analysis is a useful way to predict the performance of an algorithm. So in many of our previous lectures, you may have seen this O notation, the order of magnitude of the algorithm. And it's really actually a measure of the growth rate in case that the input doubles, what will do the growth rate? Does it double with the input, or is it a constant, or it's quadratic on the input? Is the double is 4 times bigger than the input, and so on, the growth of the input, and so on. Also in the previous lectures, we introduced classic data structures like lists, stacks, queues, priority queues, sets, and maps. And we applied them to solve some problems. But we didn't actually reason that much about when to use different data structures, except the requirements of those problems. And today we'll actually learn the efficiency of these data structures. We will also use those data structures that we learned last time to actually develop more algorithms using techniques. And algorithmic techniques like dynamic programming, divide and conquer, and backtracking are basically ways to solve problems. They are really not a programming issue, but actually a way to solve a problem, an algorithmic approach to solve problems. So how do we measure the speed of various algorithms? Like for instance, suppose that we have linear search and binary search, and we covered both of them in our previous lectures. Basically, linear search for a key in an array, it will go element by element from the beginning to the end. Binary search only works on sorted arrays. Basically, we compare the key, the element that we are looking for, with the element in the middle, and then depending if it's less, equal, or greater, we basically make the array shorter, discard half of the elements, or even return that we found the element. Now, the question that we want to answer to is which one is better for this specific problem for sorted arrays. And one possible approach to answer this question is actually to write the algorithm, pass it an input, and measure the time, the execution time that this algorithm will take on a specific machine. But there are many different problems with this approach. In some cases, it's actually used, don't get me wrong, because basically it's the real time that you get for that specific input for that specific algorithm. But it's very dependent on the specific input. So for instance, we wanted to compare linear search and binary search. If the element that we want to search for is the first element in the list, then linear search will finish immediately in basically one step, does one comparison, it's equal, it returns that is the index 1. And it will tell us, and of course it will be faster than binary search, because binary search will compare the key with the element in the middle of the array, then it will compare with the element at the quarter of the array, and eventually after a logarithmic number of steps, log in base 2 of the size of the array, it will return the index 1. So linear search for this specific input is better than binary search. Binary search will give us basically the index in a log of n, the size of the list or the array. But of course, in general, that's not true. For a sorted array, we would like to use binary search. So basically all that this tells us is the execution time measured as basically the time that it takes to run the program is not a good measurement because it's very specific for an input. If the input is different, basically in the worst case, linear search will be the length of the array, binary search will be log of the length of the array, which is much smaller. Logarithmic times are very efficient as opposed to linear times. The second issue of running the program just and measuring the time is that there are many different tasks that run concurrently on a computer. And you also have multiple threads or multiple cores. And for instance, if you look in Task Manager, or basically you have a number of cores on your computer, and if there are many programs that run in parallel, for the two different problems, for the two different runs, you will get comparatively different time. And it's not fair for an algorithm to be measured in parallel with other tasks based on the execution time. So execution time for a particular program on what is called the wall time is dependent on the system load. How do I hide this thing at the top? Is there a way to hide it? Probably you don't see it, but I do see basically, it doesn't matter. But I see the zoom top over my title. Anyway, so algorithms efficiency is usually measured with what is called the big O notation, which is also called the growth rate. And the reason for that is that it's difficult to compare algorithms based on the execution time. And therefore, a theoretical approach was developed to analyze algorithms independent of the computer system load and specific inputs. And this was basically developed by many different computer scientists, but Donald Knuth is the main one that basically developed a lot of algorithms and measured them with the big O notation. And this approach is based on the change on time versus the size of the input. So this is called the growth rate. Basically, in this way, you see how fast an algorithm's execution time increases as the input increases. So you basically compare two algorithms not on their execution time or on specific inputs, but you examine their growth rates. If you double the size of the input, what is the result in the number of comparisons or the number of steps that the algorithms executes? So we'll start with a simple problem, the linear search versus binary search algorithms. So for linear search, let's assume that you get an array of size n. And to remind everyone, linear search, basically linear search is a method that takes an array and of integers in this case and a key. The type of elements is really not important. But the way that linear search is implemented is that you have a for loop that iterates over the indices of the array from the first element to the last element. You can write it with a for loop over the indices, but you can also write it with a for loop or for each loop over the elements of the array. You compare the key with element at the current position, at the current cursor, and if it's equal, you return the index. Otherwise, after you compare the key with all of the elements in the array, you return -1. So let's analyze the number of comparisons that this algorithm basically makes. So the algorithm compares a key with the elements of an array sequentially until the key is found, or you exhaust the array. If the key is not in the array, it requires n comparisons. That's the worst case, that you went over all of the elements and you haven't found the key, or the key was the last element. If the key is in the array, then it can be the first element, the second, and so on up to the last. On average is n over 2. You basically are, it's possible that you will find the element with equal probability right in the middle, that you basically could find it at the beginning or at the end, but on average, you need n divided by 2 comparisons. So the execution time of this algorithm is proportional with the size of the array. If you double the size of the array, you expect the number of comparisons to double. On random arrays, we talk about the most general random case. So the algorithm in general grows at a linear rate. If you double the array, you will double the search. And if you double that size again, you again double the search. It's linear in the size of the array. And this especially it's already shows the fact that for an array of size n, you need on average n over 2 comparisons to find the element. And this is what computer scientists call the big O notation, or order of magnitude. So for an input of size n, you need an order of n to find the element with linear search. So using this basically notation O of n, it basically tells us that this is order of n algorithm. It's a linear algorithm for binary search, for linear search. Now, what exactly is that number? It's really the growth rate. It's not what is the best time or the worst time or the average case for finding an element. So basically, now if we backtrack a little bit, for any algorithm, there are inputs that give you a better time and inputs that give you a worse time. So an input that results in the shortest execution time is it's called the best case input. Like for instance, for linear search, if the element is the first element in the array, that's a best case. It gives you immediately the index of that element. But for other algorithms, it's something similar. For binary search, if the input is the element in the middle of the array, that's also the shortest execution time. So that's a best case input. An input that results in the longest execution time is the worst case input. And probably the best example here is if the element is not in the array. It doesn't matter that you are using binary search or linear search. Since it's not in the array, you have to basically execute the whole algorithm until the method finishes. So for linear search, you have to compare the element with every element in the array. For binary search, you have to compare it with the element in the middle, then at the quarter, then at 8, and so on. So after, with the logarithmic number of elements, because you basically take the element in the middle, then at a quarter, then at an 8, and so on. However, neither best case or worst case are representatives. So what we would like is something like an average case, but average case is very difficult to actually, and there are an analysis of average case. In fact, we will do such an analysis next class, actually 2 classes from now, when we talk about sorting, in which the average case complexity is n log n, but the worst case complexity is actually n square. So there are algorithms that average case is better way to approximate the execution time for that specific algorithm. But it's very difficult to make such basically computations. In general, the worst case analysis is what we are using for comparing algorithms. And the reason why we are using the worst case analysis is that it guarantees that the algorithm will never be slower than the worst case. Okay, so if the worst case, like in binary search on a sorted array, is log of n, where n is the size of the array, it basically tells us that you cannot do it worse than that. Log of n is the worst time that you can get for binary search. So basically, in most cases, we'll talk about worst case analysis. In some cases, we'll see that average case analysis is better because it tells us in average how often we will basically get the worst case versus an average case. And merge sort is such a good algorithm, and quicksort. Quicksort in general basically has an average case that is quadratic. It has a log linear average case, but a worst case that is quadratic. So we'll basically see average case analysis in the case of quicksort. Worst case analysis is also easier to obtain because we will learn a methodological way to actually find this worst case input and the worst case time or big O notation. So in general, we'll conduct our analysis using the worst case. By the way, anytime you want to ask a question, you can just unmute yourself and I can take out the questions, because I have no idea where the chat is in this interface. Okay, it's somewhere, but okay. Oh, thank you, Josh. So I guess that I cannot get rid of that. That's another reason why Zoom is not the best. Okay, good. Now, another issue is that we are using the rate, the growth rate for measuring algorithms. So multiplicative constants are going to be ignored. And the reason why is that the growth rate does not depend on the multiplicative constants. So basically what we can see here from this figure is that, let's assume that there are several algorithms and these algorithms have a runtime which, or the number of comparisons, steps that you are going to execute, all of them as n multiplied with a constant. So like for instance, we have linear search, let's take it as an example, which basically for 100 elements in the array, it will take 100 comparisons in the worst case. Similarly, for 200 elements, it will take 200 steps. So in this case, we can see that the growth rate, if we double the size of the input, it will double the time that it takes to run the algorithm. Now let's consider that there exists some other algorithm, maybe a mirrored array that we only have to look at half of the elements. So for 100 elements, in the worst case, it will take 50 comparisons. For 200 elements, since the array is mirrored, in the worst case, it takes 100 comparisons. We only have to compare the first half. But if we are looking at the growth rate, we can see that basically if we double the size of the input from 100 to 200, we also double the size of the number of comparisons from 50 to 100. So basically the growth rate is still 2, no matter if we divide the number by 2 as the function of how long it takes this algorithm versus the input. And now let's consider that we have an algorithm that takes 100 times the size of the input. So let's say that for every element we do 100 steps, whatever those steps are. So for 100 elements, it will take 10,000 steps. For 200 elements, it will take 20,000 steps. However, we can see that if we double again the size of the input from 100 to 200, the number of steps that are executed in the algorithm also doubles from 10,000 to 20,000. So really, the growth rate is the same no matter what is the multiplicative constant that is multiplied with the size of the input. So basically, all of these have the same growth rate, O of n, because O of n is equal with O of n divided by 2 and is equal with O of 100 multiplied with n, and so on. So the growth rate does not directly translate in the number of steps that the algorithm takes. Also, it also tells us that the speed that this algorithm will execute is not dependent on that multiplicative constant. Basically, it's only dependent on the number of basically the most important variable that it is basically in the size of the input. So in O of n is the same with O of 100n or O of a million n, because really as n becomes larger and now databases are larger and larger, the constant that we are multiplying with n is not that important. It's not always true in real applications, but in this basically most applications you are looking at this theoretical order of magnitude, not at the actual number of times that you are executing. So in the case of linear search, the algorithm that we saw before, it requires n comparisons in the worst case and n over 2 comparisons in the average case. So basically the same number n and the same big O notation is in both cases. So the growth rate, the big O notation is the same, no matter if you're looking at the worst case or the average case, it's still O of n, because that multiplicative constant can be omitted. Now, as we will see in quick search, it's not always true that the worst case complexity is the same with the average case complexity. But in most algorithms, this is the case. We are looking at the worst case complexity, but really we are getting the average case complexity. Another term that we should ignore when we basically look at the growth rate are non-dominating terms. So basically, if you have a number of steps in an algorithm, like for instance, you execute a step that takes n, the big O of n, order of n, and another step that takes n square. N square is growing much faster than n. So n is really a non-dominating term. When we are talking about 1,000 or 1 million, the square of that is much bigger than the value of n. So basically the non-dominating terms are not important. You should not consider them when you compute the big O notation. Now, the example here is a simpler example. So consider that we write an algorithm to find the maximum in an array, and the array has n elements. If n is 2, you only need to do one comparison. You compare the first element with the second, whichever is bigger will be returned. So you need one comparison, one if statement that compares the two elements, and then on a one branch it returns the maximum, on the other branch it returns the other maximum. So you need one comparison for two elements. If you have three elements, you can do it in two comparisons. Basically, you can assign one of them as the current minimum, and then you compare the current minimum with every single other element, and you update the current minimum in case that you don't have the current maximum, sorry. So in general, it will take n-1 comparisons. So if we really want the number of steps that are executed for a specific algorithm, that would be n-1. But n is really big. The input to such a function could be 1,000, could be 1,000,000, could be 1,000,000,000. So really the fact that you subtract 1 out of that input has no significance with the efficiency of the algorithm. So basically, as n grows larger and larger, the end part in n-1 dominates the 1, basically dominates, and that -1 plays no role. So when we talk about the big O notation, we are only interested in the dominating part, like the biggest value that has the highest growth rate. All the other values are much smaller, and as the input becomes bigger and bigger, the other either constants or smaller ranked orders of magnitude are not important. So for instance, for maximum number in an array, we still say that it's a linear time complexity of n. We don't look at n-1, that's not important in the order of magnitude for the algorithm. The big O notation, basically, it's also used when we have a constant as basically the number of steps to compute an algorithm. So if the time that it basically takes to execute the algorithm is independent of the input size, then the algorithm takes a constant time. So for instance, if a method returns the first element of an array, no matter what is the size of the array, you only need one step. But in general, you need a constant time to return the element. You don't need to execute a random a variable number of steps based on the algorithm itself. So basically, we call such an algorithm a constant time algorithm, and we write it as O of n as the notation. Similarly, for retrieving an element at a given index in an array. So arrays are sequential structures where every element has the same size. So if you want to return an element at a given index, the number of steps that are executed is constant. Basically, you add to the address of that array the size of an element multiplied with the index, which basically gives you an offset from the beginning of the array, which you add to the reference that is the beginning of the array, and it gives you the address of the element that you want to return. But all of these were a constant operation. You do a multiplication, an add, and then you get the address of that element.
So, Professor, regardless of what that constant time is, you call that O1, or do you call it O of whatever that constant time?
You call it O1.
Okay.
So regardless what that is, it can be 100, but always you execute 100 steps. So it doesn't matter what that number is, constant time, and you return O of 1. Okay. So for instance, for an index in an array, you would do 2 or 3 operations. You basically have to retrieve the reference for the array, multiplication between the element and the size of an element and the index, and then an addition. And that will give you the address of that element. But we are not saying O of 2 or O of 3, we're saying O of 1, and that's it. Now, this big O notation is usually used for time complexity, but really you can measure anything that it's related to an algorithm with the big O notation. Like for instance, the space complexity, how much memory is needed for that algorithm. And that can also be basically measured using the big O notation. So for instance, the time that it takes, the space that is taken by the algorithm to find an element in an array is the size of the array, because you only store the elements of the array and the extra element that is the key that you're looking for. So most algorithms basically that we are going to talk about are O of n in matters of space complexity. But there are also algorithms that in which you experience a different growth, maybe quadratic in the size of the input that you need space for storing the intermediate results or the final results that you are going to return. So basically it's the same idea of growth rate. If you need an exponential, a different function on the number of elements that will be stored in memory on the space complexity, then you basically will have a different value for basically the size. So for instance, let's assume that you're getting 2 arrays and you want to deliver a matrix of the 2 lengths as the sizes of the 2 dimensions of the matrix of elements that are the first element in the first array multiplied with every single element in the second array as basically the products of elements with indices as the row number and column number. So for that, you would have a space complexity that is quadratic. For an array of 2 arrays of input of n, you would need O of n square for the space. So space can also be, complexity can also be measured in terms of the big O notation. In most general, the space complexity for the algorithms that we're going to talk about is linear, O of n. Also, before we actually do a couple of algorithms, computer complexity, a set of useful mathematical summations that will be useful for us are the following. So the first one is an arithmetic sequence, 1 plus 2 plus 3 up to n is equal with n multiplied with n plus 1 divided by 2. Now we can always see that if there is a nested loop, like a for statement, let me write it down. We have a for statement for some integer I, which varies up to n, and I is incremented one at every step. And then we have another for statement for I equal 0 for j equals 0, as long as j is less than equal with I. And then we have j plus plus. And whatever we are going to do here, maybe we have a sum that is incremented with the element at index ij. Okay. The algorithm, this algorithm for I equals 0 will execute the inner loop once. For I equal 1, we'll execute the inner loop twice, and so on. So really the number of steps that this algorithm takes is 1 plus 2 plus up to plus n. But in total, this is also called the Gauss formula, is n multiplied with n plus 1 divided by 2. which is n square, let me just write it like this, divided by 2 plus n divided by 2. But as we said, first of all, we get rid of the non-dominating terms, and n grows much slower than n square. We also get rid of multiplicative constants. N squared divided by 2 is the same with n divided by 2. So n squared. So basically, the cost of this algorithm, of these nested loops, although we are iterating up to I instead of up to n, is O of n squared. Okay. So this is a standard mathematical sequence that is going to be used for many algorithms. Another interesting mathematical sequence are the geometric sequences. And we are going to look directly, actually, let's start with the general case. You have A as basically a value, and then you have powers of A. So A to the power 0 plus A to the power 1 up to A to the power n. The sum of those is A to the power n plus 1 minus 1 divided by A minus 1. Most cases we'll have two binary search trees. So we have two branches, and on each branch we have two branches and so on. So the same sequence, geometric sequence for A equal 2 will be equal with 2 to the power n minus 1 minus 1, because n minus 2 minus 1 is 1. So this is really divided by 1. And this is an exponential function. So basically the sum of all of the powers of 2 is really 2 to the power n plus 1 minus 1, which is O of 2 to the power n, if we are looking at the big O notation. Okay, so we'll determine the big O notation for various algorithms. We'll start with simple repetitions, then sequences, selection, like if statements, and then those algorithms that can be reduced to logarithmic times. And we start with a simple loop. So let's assume that we have this loop for every I equal 1. As long as I is less than n, we increment k with 5, and then we increment I with 1. And the number of steps that are executed for such an algorithm, for this loop, for every from I equal 1 to n, included n, since we are only incrementing I once per loop with 1, will be executed exactly n times. Now, the interior part of this algorithm, the body of the for loop, it takes a constant time, because basically it doesn't matter how complex is this formula, we are adding 5 to k and we are assigning it back to k. It could have been multiplications, divisions, anything that involves constants, and really it's a constant time. Let's call it c. The time that it will take for n, basically n number, the value of n, that's t of n, the time complexity of this loop, is the constant c, that is to do the inner operation, like in this case, summation followed by assignment, multiplied with the number of times that we are going to do it. And in this case is n, the number of times that we execute the loop. So this will be equal with c multiplied with n, but again, because c is a constant, it will take constant time to add 5 and assign it back to k, we can ignore it. So we'll ignore the multiplicative constants, and we are getting that this algorithm has a growth rate of n. So in big O notation, O of n is the time efficiency of this algorithm. Okay. And if you're looking at a simple algorithm that does exactly that, if we are basically assigning the current time in milliseconds to a variable start time, and then we have our algorithm that iterates n times and increments basically k with 5. And we vary n from 1 million to 1 billion, we will see that is linear. Basically, if the input is 10 million, the number of milliseconds is 61. I just ran it on my computer before the class, And it basically took 6 milliseconds for 1 million elements, or n equal with n 1 million, 61 milliseconds, so 10 times, almost 10 times, around 10 times bigger for an array for n equal 10 million, basically 10 times bigger. For n equal 100 million, it will take 610 milliseconds. So basically, it's linear with the size of the input. If we make the input 10 times bigger, the execution time is 10 times bigger. So really, this is linear growth. As you are growing, the algorithm is 10 times bigger. And if you want to plot the execution time versus the input size in the Cartesian plane, you will get something like this. So if this is the execution time on the y-axis, and this is the growth, the input size on the x-axis, the execution time basically is somewhere like this. Basically, it's linear, it grows linearly in the size of the input. Okay, so it's very direct growth. And yes, the slope will be different based on the constant c, but it's still linear. We are looking at the linear growth. Now, what about nested loops? So we have a for loop that iterates from I equal 1 to n. And in an inner for loop that iterates for j equal 1 also up to n, we can see that inside the block of this for loop, there is another constant number of operations. We are adding I to k and then j to that sum, and we are assigning back to k. So the inner loop will take n times for every value of I. So if I equal 1, the inner loop will execute n times. For I equal 2, the inner loop will execute n times. Now, how many times the outer loop will execute? It will execute n times. So the entire number of times that it basically takes to execute the entire code, the 2 for loops, is basically a constant c, which is the time that it takes to execute the body of the for loops, multiply with n for the number of times that it takes for every I for executing the inner loop, and the number of times that it executes the outer loop, which is also n, because I varies from 1 to n, which is equal with cn square. But again, we can ignore the multiplicative constant because in growth rate, it's immediately dropped. So the time in big O notation that it takes to execute this block of code, these 2 nested loops, is n square, O(n) square. This is called quadratic time. And it's called quadratic because if you have an input of a given size and you double the size of the input, the time that it takes to iterate over the entire structure will be 4 times bigger. So it's a quadratic algorithm. Okay. But one thing before I continue, both linear times and quadratic times are basically in the same class of basically algorithms that you have either n or n square or n cube time to execute. Okay, so now we modify a little bit the algorithm. So instead of iterating in the inner loop up to n, we are going to iterate up to I. So if we are looking at how long this algorithm will take, the inner loop will execute I times. So now for I equal 1, it will basically execute once. So it's only one constant that is added to the real execution time. For I equal 2, it will execute twice because it starts with j equal 1. And as long as j is less than 2, it will execute by incrementing j once only. So it's 2 multiplied with the constant time that it takes the inner block. For I equal 3, it takes 3 times the constant, that time that it takes the inner block. And this continues up to I equal n, for which the time to execute the inner block is n times the constant time. So now we can use the first arithmetical sequence formula, that this is equal with c multiplied with n multiplied with n plus 1 divided by 2, which is equal with c divided by 2 multiplied with n squared plus c divided by 2 multiplied with n. Now n squared grows much faster than n, so the second term is a non-dominating term and it will be ignored. And in the first term, the constant, the multiplicative constant, can be ignored because it has no effect on the growth rate. So the growth rate, the big O notation for this body, these two nested for loops, is n squared. So again, after dropping the multiplicative constants and the non-dominating terms, we are getting the same n squared that we got when we looked at iterating n times. Okay, so really what the big O notation measures is the growth rate, not the actual time that it takes to measure the algorithm. So next, if the inner body of this loop is executed 20 times, so it doesn't have any, it's a constant, it has nothing to do with the value of n. As n grows, this 20 becomes insignificant, because if n is a billion, the fact that for every element you are executing a loop of 20 times is not important, because the growth rate is a variable, it's variable of the size of n, not the size of 20. Like in the case when we had the value of n multiplied with a constant. That didn't matter if that constant was 2, or it was 1, or it was divided by 2, or multiplied with 100. The constant is not important. So if we want the time complexity, it will be 20 multiplied with the constant c for the inner block, everything multiplied with n, because we repeat this inner for loop for every n. But this is 20c multiplied with n. 20c is a constant, so again it can be ignored, because really the growth rate is a linear growth rate. If we double the size of the input, the execution time doubles. So this is a constant that doesn't play any role in the growth rate. So again, it's O of n. What if we have multiple parts of our algorithm? We have a part of the algorithm which basically iterates from j equal 1 to 10 and executes some operation, some constant operation. And then we have a part that iterates from I equal 1 to n and an inner loop that executes 20 times. So we already computed the efficiency of the inner loop. That was O of n. The outside efficiency is exactly 10 steps. So if we compute the entire algorithm, it will take basically 10 times some constant, which is to add 4 to k, plus 20 multiplied with the constant time to add I and j to k and assign it back to k. And this is executed n times. So here we can see that c multiplied with n is just, it's much smaller than 20 multiplied with c multiplied with n. As n grows, c multiplied with 10 is still a constant. It's not basically going to grow ever. Now 20 multiplied with c is a constant. So again, we can ignore it. And therefore, the growth rate will be the big O notation in n. It's also a linear algorithm. And this was the same if you have an algorithm that takes n or big O of n and big O of n square. The n square is the dominating one, and it will dwarf the existence of the linear time. Now, if we have if statements, so if statements basically have multiple branches, and we want to compute the execution time in the big O notation of the entire if statement. It's dependent on which branch. So let's assume that we have least if a list contains an element and this list is implemented with an array list, let's say, the time to find the element is done in linear time. It's a linear search algorithm. So basically it will give us an O of n. Once we find the element, either we find it or we don't find it, we execute the body of that if statement. So in the case of the true part of the if statement, it takes O of 1. But in the case of the else part, we iterate over the elements in the list and we print every single element. So the time that it takes for the else part is O of n. So now what is the time to execute the entire if statement? So it's basically the maximum between the two branches. So it's basically the time complexity for this if statement is the test time, which was O of n, plus the worst case on both if and else branches. On the if branch, we have 1. On the else branch, we have n. So O of n will be the worst case because it's the worst case, it goes on the else branch. Now we have O of n followed by O of n. So it's a sum of the two growth rates. But you're basically summing, it's kind of like in the non-dominating term case. You have O of n and another O of n sequential. So in growth rate, it's still n times bigger. So it's still O of n. So this is arithmetics for growth rates or the big O notation. And there are many others that we can actually learn. Like for instance, let's say that an algorithm takes quadratic time, but the pre-processing of that algorithm takes linear time. The result of adding these two steps, sequential steps one after another, is the maximum between the two. So it's basically going to be just the quadratic time. So if you have multiple steps on your computation, the bigger one is the one that beats all of the other steps. Okay. Now, logarithmic time. So suppose that you want to compute a big product multiplying a some number n times. So the first algorithm that you would write is that a product a variable result is assigned 1, and then for every I from 1 to n, including 1 and including n, you multiply the current result with a, and you do it n times, and in the end the product the result will be n to the power a to the power n. So basically you multiplied n times the same value a. Without loss of generality, you can assume that n is equal with 2 to the power k. So you can choose that n is a power of 2. Like for instance, 2 to the power 4, 16. Or 2 to the power 8, or 2 to the power 16, or any power of 2. So multiplying a n times, it's basically you have a product of a with a up to a n times. But without any loss, you can group these a's. So you can group a multiply with a in one product. Then you can multiply with itself. So you get a multiply with a multiply with a multiply with a. Then you can multiply that number with itself. So again, you will basically get the product a to the power 4 multiplied with itself, a to the power 4, and so on. But there is a better algorithm that we can do for such a case. So if we can group the a's in this way, then we can actually write a better loop, a loop that iterates from I equal 1 to k, where k was the logarithm base 2 of n, where the result, which was initially initialized with a, is equal with the result multiplied with the result. So basically, when the result is a, it will multiply a with a. Then in the next step, it will multiply this product with itself. Then the next step, the product that we currently have in the result, it's multiplied with itself again. And this only has to be executed k times. So the time that it takes to execute an algorithm that computes exactly the same value is k number of times, which is log in base 2 of n, which has a growth rate of log n. It's also called log time or logarithmic time. It's basically an algorithm that is logarithmic. And there are many algorithms that have this behavior, logarithmic behavior. And the best one to consider is binary search. So just to remind everyone what is binary search. You get as inputs a sorted list, a list of integers that is sorted, and one integer. And you want to find if that integer is in that list. You start by initializing two ranges, the low range starting with 0 and the high range starting with the index of the last element, the length of the list minus 1. While the high is greater than low, you compute the index of the element in the middle, which is low plus high divided by 2. If the key is less than the element at index mid in the list, then the high is set to middle minus 1. If the key is equal with the element in the middle, then the middle is returned. Else, the low is assigned the middle plus 1. So basically, you are restricting the search area with half of the elements of the remaining array at every step. So you compare in the first case, you have the range from 0 to the length of the array minus 1. That's the value of low plus high. You divide that by 2, you get the element in the middle, the average, which is basically the length of the array minus 1 divided by 2. Now you compare the key with the element at middle index. So basically, if it's less, you can immediately discard the second half of the array, because by transitivity of greater than relationship, if the key is less than the element in the middle and the element in the middle is less than all of the following up elements because the list is sorted, you basically can reduce now the search to the index of middle minus 1. So you are bringing the search from the end back to the middle. So you got rid of half of the elements in one step. And you continue this while loop. So in the next step, you get rid of, again, half of the elements that are left in the search space. And in the next element, again, we'll get rid of half of the elements in the search space, and so on. The moment that you find the element, you return it. So the algorithm for binary search is you're looking for a key in a sorted array. At each iteration, you have a constant number of operations. You basically compare the element with the element at the middle index, and you decide what to do next. You can subtract, you can basically assign a different value to the high or a different value to the low index, or you can return that you found the element. Now, we denote with T of n, in all cases, the time complexity for the algorithm. And we assume, again, without loss of generality, that the number of elements in the array is a power of 2. So it's 2 to the power k, okay? Therefore, k is log in base 2 of n. Now, binary search eliminates half of the input at every step. So T of n, for the time that it takes to do binary search for n elements, will be based on the algorithm of binary search, the time that it takes to search in half of the elements after you move the index of the range to the middle, either low or high, plus the constant time to do the comparison, basically, and to compute the index of the middle element and do the comparison. So basically, T of n is T of n divided by 2 plus C. But now, this T of n divided by 2 can actually be computed in the same way. You search in half of the remaining of that array, which is basically n divided by 2 to the power 2, plus a constant time. And you add also the constant time for the last step. And you continue this, and how many times you continue it? You continue it until you have a single element, until you basically, after k steps, you have n divided by 2 to the power k, which is 1. You found a single element, and then you basically return. So how many, what would be the value of t of n is basically 1, the constant time that it takes for finding the element in a single element array, plus c multiplied with k, but k was logarithm base 2 of n, so it's basically c multiplied with logarithm base 2 of n. And again, if you eliminate the non-dominating terms and the multiplicative constants, you are left with O of log in base 2 of n. So basically for binary search, you reduce the space by half at every step, and that guarantees that in logarithm in base 2 of n, you will find the element. Okay? So the maximum, the worst case complexity is that you have to compare the key with n logarithm base 2 of n other elements. You don't need to compare it with all the elements. You need to compare it with logarithm base 2 of n elements. And that's why the complexity of binary search is logarithmic, it's not linear. So an algorithm with logarithmic complexity is basically a good algorithm. The base, it doesn't matter, because again, when we talk about growth rates, logarithmic complexity is logarithm in any base, really. It's kind of like the non-dominating terms. Now, it also grows very slowly. If in the case of binary search, each time you double the array, at most one comparison is required. So you double the array, all that you need to do is to compare the element still in the middle and then discard half of the array. So growth rate basically means that if you double the size, you only need one more comparison. If you square the input size, then you will only double the time of the execution. So basically, it's a very efficient algorithm. Linear binary search or a logarithmic algorithm is very, very efficient. Selection sort. So this is the algorithm for selection sort. If you remember from last semester, we iterate over all of the elements from the beginning to the end. For every element, we find the minimum between the index of that element up to the length of the list by assigning first to the current minimum the element at least I, the current minimum index you assign I, and then you iterate from I plus 1 for j up to the length of the array. And if the current minimum is greater than the element at index j, then the current minimum is assigned the element at index j, and j is assigned to the minimum index. In the case that the current minimum index is different than I, you need to swap the elements at index I and current minimum index, which is done here. First, I assign the current minimum, the element at index I to the element at current minimum index, and then the current minimum is assigned to the element at index I. So what's the complexity? Basically, for n elements, you have to execute the inner loop, which finds the minimum element. So for the first element, you would need to do n-1 comparisons. You have to go in the rest of the array to find which is the minimum. For the second iteration, you need n-2 because you already found the minimum, you put it at the beginning, from now on you ignore it. You look at the next element and so on. So if we compute the Tn, the time to execute for an array of size n, it will be n-1 steps for the first element, plus a constant to basically do the swap, plus n-2 for the second element, plus a constant, and so on. And that is basically, again, we have the same arithmetical sequence that we saw before. It's 1 plus 2 plus 3 up to n-1, which is n minus 1 multiplied with n minus 1 plus 1 divided by 2 plus n minus 1 multiplied with a constant c, because for every element you had to do the swap to check if you have to do the swap. And this is equal with n squared divided by 2 minus n divided by 2 plus cn minus c. But the dominating term here is the square, n square. So all of the others are discarded. And then you discard the multiplicative constant and you're getting that this is on square. It's basically a quadratic algorithm. So selection sort is quadratic in the worst case. In fact, in any case, because if you're looking at the average rate, you still have to do all the steps. There is nothing that you didn't need to do. So this is a quadratic time, and it's not as good as linear or log time. Basically, it's much worse. Many algorithms are quadratic, which basically means that if you double the input size, the time will quadruple. And that's not basically 4 times bigger than the previous time. Insertion sort is very similar. So again, we have here the insertion sort algorithm. You start from the beginning, and for every element, you consider the prefix sorted, and you want to insert the current element in sorted order. So let's take some random index I. So you want in list of I to be inserted in the sorted order of the elements between 0 and I minus 1. So basically you first have to find the position. You start from the beginning, and as long as the list at element at position pos is greater than the element at index I, you if it's less than, you just continue executing the for loop. The moment that the element at that position becomes greater than the element at index I, you break that for loop. So in the worst case, you have to execute n steps. Then you need to shift the elements. So you found the position where it has to be inserted. You go to the end of the currently sorted array, which is at index I, and you go downwards and you swap the element. You basically shift the elements from left to right, from the end. So basically you start shifting the elements up to the position pos, the position in which you wanted to insert the element that was originally at the position. So again, if we need to analyze the execution time for insertion sort, basically you have n times that you execute the outer loop. And in the worst case, you are going to execute k time, where basically k is the current element index number, after the kth iteration, you have an element, an array of prefix of size k, and you have to do at most k comparisons and shifts. So basically for the end, you have n minus 1 plus a constant, then you have n minus 2 plus a constant, and so on up to the last element, which basically you need to insert it in sorted order. So ignoring everything that is basically non-dominating, like constants and smaller terms, again, the complexity will reduce to n square quadratic algorithm. Before we continue to Towers of Hanoi, let's see if there are any questions. And for that, I assume that I have to open the chat, which is right here. Okay, so one good question is, why did we all do, in the case of binary search, and even before binary search for this algorithm, why do we always say without loss of generality? Okay, so in the case that you are somewhere, and let's actually come here. So you want to compute binary search for an array that has a size of 2 to the power k k. It's somewhere between, let's say, 2 to the power k minus 1, and it's bigger than that, but it's less than, or it's bigger than that, and it's less than 2 to the power k. Okay. So the number of steps that you would execute is basically like in the case of this algorithm that we described here, is the biggest size would be for 2 to the power k. So for that, in the case of a logarithmic algorithm, like for instance this product, it will take you k steps. Okay, worst case, k steps. Now, let's say that is not, n is not equal with 2 to the power k. It's somewhere between 2 to the power k minus 1 and 2 to the power k. So now you need to basically eliminate the factors that you didn't want. So out of the k steps, you need to backtrack some number of steps. In this case, it would be basically 2 to the power k minus 1, because basically the difference between these two numbers is 2 to the power k minus 1. Okay. Now, you can do it in the same algorithmic way that you did before. In the case that you basically have a binary search, you would do it by comparing the element in the middle and so on. So really, you should look at what is the growth rate in the worst case, which is k steps. In the case of binary search, so if the last elements, if there are more elements than 2 to the power k, but still less than 2 to the power k, is there are more elements than 2 to the power k minus 1, but still less than 2 to the power k, you can fill the array with the last element for the rest of the array up to when you have the size 2 to the power k. So basically the idea is that if you can do for a bigger array the same algorithm in log of n, you would still do it for a smaller array, something that is not as big as 2 to the power k, but it's between 2 to the power k plus minus 1 and 2 to the power k. So really, basically, it doesn't matter that it's a power of 2. It's just that it's easier to understand it when you are looking at these powers of 2 to compute what is the efficiency of the algorithm. There is no reason to choose 2 in particular. You can choose 3. The base of the logarithm is not important. So for instance, you construct instead of binary search, ternary search, let's call it. So you compare with the element at a third and the element at 2/3. It's okay. You still discard 2 of the slice of the 3 slices. So basically you can consider the elements from index 0 to 1/3, from the elements from 1/3 to 2/3, and 2/3 to end of the array, but you can still discard more than you actually have to continue searching. So the base of this logarithm is really not important. You can actually break the slices into 10. Still the cost of the entire algorithm for this searching algorithm is logarithmic. So in base 2 or in base 10 is the same. In fact, one thing that you may have seen already is that I dropped the base. I don't care what is the base. It's still logarithmic time. Okay, good. Okay, so I think we don't have time actually for seeing the cost for towers of Hanoi and Fibonacci. So we will stop here today, and we'll continue with the towers of Hanoi next class. Okay, that's all for today. Before we stop, let's discuss the quiz for the class. And for that, I need to find the quiz. So what's the number of iterations that it takes for this loop? And then let me increase the size. So in this loop, for n, some n that is an input from the user, I have a count that starts with 1. And then at every step, the count is multiplied with 2. So let's say that n is 100. I start with 1, count is multiplied with 2, count becomes 2. Then count becomes 4, is still less than n. Then count becomes 8. Then count becomes 16. Then count becomes 32, 64, and then it becomes 128, which is not less than 100. So how many steps? We saw that we actually were jumping double at every step, which basically means that that the time is a logarithmic time, because for any n, the number of iterations up to when the moment that n is not greater than count anymore is logarithmic base 2 of n, because the count, at every moment you multiply with 2. So basically you are gaining double the number of steps that you did up to now at every step. Okay, so the worst time complexity is logarithmic base 2 of n, and that's a good example for logarithmic algorithms, that you started with a simple loop, but the number of iterations is logarithmic base of n, of base 2 of n. Another simple algorithm, we have 3 nested loops. K iterates from 0 to n, I iterates from 0 to n for every k, and j iterates from 0 to n for every I. So we execute n times for every I, n squared times for every k, and n cubed times for the value of n. So it's a quadratic, it's a cubic algorithm of n to the power 3. Then what's the time complexity of this algorithm where the inner loop iterates up to I instead of n? And we actually saw that is quadratic, is n to the power 2. Same algorithm, we have 2 for loops, one for loop that iterates n times, where n is the size of the array, and one that iterates in reverse order n times. The sum of 2 of n's are still O of n. So basically this is still a linear algorithm. Using the big O notation, we also want the size of this algorithm, and again we have up to I. So this is a arithmetic sequence that executes once for the first step, twice for the second step, and so on up to n times for the last step. So the number of steps in total will be again n squared. Now, I want an algorithm that computes the sum of all the integers from sum n1 to n2. And by default, you will write the following algorithm, one that writes a for loop from n1 to n2 and adds every number to the sum. The complexity of this algorithm will be n. Basically, the worst time complexity will be the difference between n1, n2, and n1. But you can actually write it as a formula. So if n is n2 minus n1 plus 1, then you can directly return n multiplied with n1 plus n multiplied with n minus 1 divided by 2. And that will give you the sum of all the numbers between n1 and n2. And all of this was done in constant time because we didn't have to iterate at all. We computed a sum of products and division, and this is done in a constant number of times, no matter what n1 and n2 are. So we can write a constant time algorithm for performing the same task. And that's the quiz that basically you have to think about. Any questions? I think that's it. Thank you very much. Let's see if actually the recording works.